All right, let's get started with this test 3 review. So we've got chapter 11, which covers probability, and chapter 12, which covers statistics. So let's go ahead and get started going through this. You got about 27 questions, half and half. So here we go. So these first few questions, I believe it's question 1 through 13. Let me double check. Excuse me, question 1 through 14. They cover chapter 11. So right here we've got a person can order a new car with a choice of 15 possible colors, with or without air conditioning, with or without automatic transmission, with or without power windows, and with or without a CD player. How many different ways can a new car be ordered with regard to these options? So again, down here it says write an integer or a decimal. This is not going to come out to a decimal. But the thing that you have to ask yourself is, remember when you started chapter 11, there are 3 ways that we can count up totals. You've got the fundamental counting principle, you've got permutation, and you got combination. So what kind of problem is this? This is one of those fundamental counting principles because you have different groups to be selecting from. You're going to select from 15 possible colors, and then you're going to pull out from the air conditioning, whether you want it or not, which I don't know why you wouldn't want air conditioning. Then you got with or without automatic transmission. Then you got another group that's with or without power windows. And then we've got a final group that is with or without a CD player. So you have all these different groups that you're pulling from. So that's the fundamental counting principle. So all we have to do is just multiply all of our options together. So we have 15 times with or without air conditioning is 2 choices. With or without automatic transmission is 2 choices. With or without power windows is also 2 choices. And finally, with or without a CD player is 2 choices. So you just go and you multiply all this out. Use your calculator. So let's pull up the calculator. We got 15 times 2 times 2 times 2 times one more 2. And that's how many different cars we can have. 240. So there you go for the first guy. So let's move on to question number 2. So it says a club with 18 members is choosing 3 officers: president, vice president, and secretary/treasurer. If each office is to be held by one person and no person can hold more than one office, and how many ways can these offices be selected? Well, if you think about this, remember permutation, it's all about order mattering. And so this is one of those cases where order matters to us because the way our club will be ran, depending on who's president, vice president, and secretary/treasurer, always different outcomes. You can also think of when you're looking at permutations, is there like a ranking system? And obviously in here, the president's the best, and you got the follow-up, and then the secretary. It's like a first, second, third. And that's always going to be a permutation. So remember with permutations, you got N, P, R, where N is how many individuals you're dealing with. R is how many you're going to select. So in here, we've got 18 individuals in our club, and we are selecting 3 positions. So we just go into our calculator and we run NPR. If you forget where that's at, you're going to hit math. That's where all of our good stuff is at. And you're going to scroll over to probability. And NPR is number 2. So you scroll down to it. And then now you just fill in your blanks. So we've got 18. Well, if I would have picked up my first one, 18, choose 3. And that's how many different ways we can fill those offices. 4,896. And there you go. Moving on to question 3. If you haven't noticed, it's been going in order of everything that we've done. So again, in here, it automatically tells you what it is, permutations. Also know that we did a word like this in class. We did Mississippi together, and then you've had some in your assignments. So how many distinct permutations can can be formed. So we are using permutations, and since it's about a word and there are repeat letters, this is where we want to do a permutation with duplicates. So if you don't remember that formula, it looked like this. You had n factorial on top, and then you had p factorial, r factorial, q factorial, blah, 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 blah. And it kept going depending on how many repeats you had. Okay? So that's what we need to run here. So when we look up here, let's count up how many letters we got. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got 9 factorial on top. So let's write that down. Actually, I could just write it up here. 9 factorial. And then we just start going through our letters. E. Does the E repeat? Yeah, we got 2 of those. So down below, I got a 2 factorial. Does the N repeat? Yeah, we got 2 of those too. So I got another 2 factorial down here. Does the T repeat? Absolutely. We got it right there. So down below I have another 2 factorial. And I don't think anybody else repeats because we already got the E taken care of. We got the R, and there's no other R's. We got an A, no other A, I, no other I. So there we go. This is all we got to do. This is what we got to run in our calculator. So again, that factorial button, it's under math. So if you hit math, scroll over to prob, there's that factorial. But before we do that, we are dealing with a fraction, so we're going to use our best friend, the fraction. Alpha y equals. There's our fraction guy that we want. Hit enter. And now let's put everything in. So we got 9. Go to math. Number 4 factorial. So there's our top. And then down below we just got a bunch of 2 factorials. Oops, I accidentally hit alpha. My bad. Math. There we go. There's our first 2 factorial. We'll do it again. Math. Second factorial. One more. And there it is. And then all we got to do is just hit enter. And boom! That's how many distinct permutations of the word entertainment we can have. 45,360. 45,360. And there we go. Just a little formula. All right, now we want to win the lottery. So one must correctly select 4 numbers from a collection of 46 numbers. The order in which the selection is made does not matter. How many different selections are possible? So if you think about this, since the order doesn't matter, this is our combination. So a combination is going to run a lot like NPR, except this time we got NCR, where N is our total amount that we're dealing with. So in this case, it's the 46 numbers. And then R is how many we're going to select, just like the NPR. So really what we're looking at is 46C4, because there are 46 numbers and we want to choose 4. Again, we just go right back to our calculator and run it in the calculator. Okay? And it's right over there under the probability. I believe this is number 3 now. So if you go to math, go over to prob, yep, number 3. So all you got to do is type in the 46, scroll over, hit 4, hit enter, and there's how many different lottery tickets we can buy. 163,185. 163,185. Let me make sure of that number again. Yes. Okay. So there we go. Flying right through this, guys. It's all pretty much straightforward. Using a lot of calculator techniques on this. Hopefully you're not trying to do this by hand. That would be just silly. All right. So now we're actually going to start diving into the probability. So everything we just covered, that was 11.1, 11.2, and 11.3. Okay. So now we're in 11.4, finding probability. So we got a 12-sided die, and we want to know what is the probability of rolling a 10. So remember, with probability, it's all about basically what you want your outcome that you're looking for over the total. It's kind of the idea behind probability. So what we want is rolling a 10. Well, how many ways can we roll a 10? Right here. There's only one way. Out of how many numbers do we have total? Right there. There are 12 outcomes. And you can see all 12 outcomes right here. So that is your bottom number. And with anything in here, it says write as a whole number. Well, that's not going to happen. This definitely has to be a fraction because it's probability for us. So that's what we're going to leave it as, 1/12. Okay? Because you will always want to reduce your fraction. And if you didn't know if that was reduced or not, you just go right into your calculator, hit alpha, y equals, enter the fraction, hit enter, and see it is reduced. So we're all good on that. Alpha y equals is your best friend in this unit, at least for chapter 11. So, question number 6. The table below shows the educational attainment of the country's population aged 25 and over. Use the data in the table expressed in millions. So these numbers are in millions. It's not like 11 people have less than, or that are males have less than 4 years of high school. That's just silly. So we're going to use the data in the table to find the probability that if we selected someone, it was a woman with less than 4 years of high school. Okay? Well, let's find that first. I need a woman, female, less than 4 years of high school. Here's less than 4 years. Here's the female. So that's the number we're focusing on. That's what we want. So that's our top number when we're thinking about this. Hey, see, there's the right directions that should have probably been on the other page, but that's all right. So that's our top number, 15. Now the question is, what's the total? How many people were there? And that's this number that's right there. There are a total of 160 people. So this is where I was saying, make sure that you know how to use your best friend on the calculator, because this definitely reduces. So you just go to your calculator, hit the alpha y equals, put in your fraction of 15 over 160. Alpha y equals 15, 160. Let me make sure that that was the correct fraction, and it is. Hit enter, and there it is now reduced. That's the fraction they want, 3 over 32. And there we go. 3 over 32. Perfect. Moving right along. See, we're already killing this. We only got like 20 more questions. All right. So Maria, Simone, Tyrone, Sarah, Ian, Dawn, and Katrina have all been invited to a dinner party. They arrive randomly, and each person arrives at a different time. So in this one, the cool thing is for this question, you had it in your assignment. Hopefully, maybe you got a chance to talk about it in class. This one, they scaffold it for you, which is awesome. So they help you figure out what it is, the situation you're looking for, which in our case is what's the probability that Maria will arrive first and Katrina will arrive last. And they're going to help you out with that. Part A is all about figuring out that total because it wants to know in how many ways can everybody arrive. And part B is figuring out what we want part, which is all about Maria arriving first and Katrina arriving last. Now in this one, it doesn't really matter how they arrive. Okay, so the order doesn't matter, and most of you would think that this would then be a combination. But if you went in and ran a combination just for the beginning, so how many people do we got coming to the party? We got 1, 2, 3, 4, 5, 6, 7 people. So if you went in and ran a combination for this, it would be 7 choose 7. And if you ran that combination, the answer would be 1, which does not make sense. There isn't just one way for them to arrive, okay? So it's not a combination, but again, order doesn't matter. So what this is the fundamental counting principle. because you have 7 guests. 4, 5, 6, 7. Kind of ran out of room. Let's slide this. Oops, come back. Scroll to the bottom. All right, let's grab all this stuff, slide it over just a little bit. There we go. So we got 7 guests. This is really fundamental counting principle. Okay? And it's all about the options of how many guests you have left to arrive. So as you look at the first guy right here, how many ways can the first guest arrive? 7, because there are 7 people. Now we go to the next guest. How many ways can the second guest arrive? Well, there's 6 people left. And it continues in that trend. The fifth, by the time we get to the third guest, there's 5 of them left. And then 4, and then 3, and then 2, and then 1. And the fundamental counting principle just says multiply all these. If you notice, it kind of looks like a factorial as well. So you could also run the factorial on this. So all we need to do is go to our calculator and take 7 times 6 times 5 times 4 times 3 times 2 times 1. Again, like I said, you could just run the factorial on it because that's what a factorial really looks like. So you could push 7, math, go to probability, come down here, get that exclamation mark, that factorial, and hit enter. All right, I'll hit enter again. Okay, I'll keep hitting enter. There we go. So there are 5,040 ways my 7 guests could arrive. Now, it's question B that we got to think about. So it says Maria arrives first. There is no other person that's going to arrive first. Maria is taking that spot. And then it says Katrina arrives last. No other person is going to take that spot. Okay? So those positions are what we call fixed. There's no changing that. But what does change, what we need to know about, is what's going to happen to all these people in here. That's the trick to part B. You don't worry about the first and the last. You worry about everybody in between. So how many guests do I have left that can arrive second? There are 5 guests because we fixed the beginning and the end. And then there's 4 for the third guest. And then there's 3 for the fourth guest. And 2 and then 1 for the 5th and the 6th guests. So all we need to do here is multiply those numbers. Or in other words, run a 5 factorial. And that will give us part B. And then we put it together for part A. Pretty straightforward. So push the 5, go to math, scroll over to probability, scroll down. There we go. 5 factorial is 120. So there are 120 ways that Maria can arrive first, Katrina last. So like I said, all we do in part C is we take that information that we found, the 120, we will slap it over to the 5,040, and of course, reduce. Because what we wanted was Maria first, Katrina last. There it is. And then out of the total number of ways was that. And again, we just go to our calculator and we reduce this information. So, alpha, y equals, enter, 120 all over 5040. Enter. And there it is. So the probability of that actually happening is 1 out of 42. 1 out of 42. So we just come up and put that in a blank. 1 out of 40 dose. Okay? Did I say 1? Yeah. Cool beans. There we go. I think this is one of the problems on this exam that kind of trips students up the most. Because you got to think about what's really going on. And it's not a combination. It's a fundamental counting principle. So right here it says a group consists of 4 men and 7 women. 5 people are selected to attend a conference. how many ways can 5 people be selected for this group of 11? How many ways can 5 women from the group of 7 be selected? And then we put it all together. So again, it's another scaffolding problem. Now, thinking about what this is it a fundamental permutation, combination? Well, if we look at what we're doing here, we're just got a group of people and we want to select them to go to a conference. Doesn't matter how I select them, so this is one of those combination ones. Because I just want like 4 people, I'd be like you, and you. So you're all going to the conference. Didn't matter how I selected them. I just needed 5 people in this case. I think I said 4 a couple seconds ago. All right, so the first thing we're going to do is, and since we know this is a combination, we're going to run combination all the way through this. It won't change. Just like in the last problem, we ran fundamental counting principle all the way through. It didn't change. So part A, it says, how many ways can 5 people be selected from this group of 11? Well, 11 is the N, 5 is the R, so we want to run 11C5. Okay, so we go to our calculator, 11, math, probability, all the way down to number 3, 5. So there are 462 ways we could choose groups of 5 from the 11. 462. Now down here, wants to know how many ways can we select 5 women. So that 5 is our R from 7. So that's our N. So we just go to our calculator. We're going to run 7C5. Not too bad. 7, math, scroll over, 1 more, scroll down, and 5. So there are 21 ways we can select 5 ladies out of 7. And then all you do for the end, again, we want the probability that the group we select is all women. So we just take what we know, the 21, because that's what we want, all women, out of the total, which was 462, I believe. Yep. And of course, go into your calculator and make sure that that is reduced. So we hit our best friend, alpha y equals. We've got, oh gosh, forgot the top number, 21 over 462, hit enter, hey, and it does reduce. So we've got 1 over 22. That is our final answer. And there you go. Well, let's move on to the next question. We're doing great. All right. So it says you are dealt 1 card from a 52 card deck. Find the probability that you are not dealt a 9. So there are 2 ways to think about this. So 1, in class, we talked about a complement. So we want not a 9. Remember, that was back from our beginning Venn diagram chapter where the little asterisk meant that it was the complement of the situation. That's what you're dealing with here. You could have also wrote not 9, all the same. Well, in order to find the probability of not 9, you're going to take 1 minus the probability of a 9. So hopefully you've been studying up on your cards. And as we go through this, we got 1 minus. Well, what's the probability of drawing a 9? Well, how many 9s are in a deck of cards? There are 4 out of 52. Okay? So if you actually subtract this, you end up finding out that this is 48 out of 52. And when you reduce that in your calculator, you should get 12 out of 13. Let's just double check. Alpha y equals 48, 52, 12 out of 13. Okay, So that's one way of doing it, and that's just running your complement formula. That's what was right here. The other way is, you could think about this logically. You can go straight to the probability. Because if you do not want a 9, well, how many cards are not a 9 in a deck of cards? Well, if there are 4 cards that are a 9, take 52 minus 4, and you get 48 out of 52. Oh, look, this number is the same as that number that's right there. So you can think about it either way. You could run your formula, or you can think about it logically. Your choice. But again, always make sure that you reduce that answer. And our reduced answer was 12 out of 13. All right. Question number 10. You randomly select one card from a 52 card deck and find the probability of selecting a 9 or a 5. When we talked about ORs are based on the idea of whether your event is mutually exclusive or not mutually exclusive. When you are mutually exclusive, it means the 2 events cannot happen at the same time. When you are not mutually exclusive, it means they can. Like, just to give you a quick example. 2 events that are mutually exclusive, if you flip a coin and roll the die, the probability of getting a heads and rolling a 1 is mutually exclusive, because you cannot, the outcome of heads and a 1 cannot happen at the same time. You got to do them separately. Okay? So those are mutually exclusive events. They can't happen at the same time. Not mutually exclusive events would be like if I was in a car accident and wearing the seat belt. Can that happen at the same time? Can I be in a car accident and wear a seatbelt? Absolutely. Those are not mutually exclusive events. So again, mutually exclusive means they cannot happen at the same time. Not mutually exclusive means that they can. So the question to you is, can I draw a card and be a 9 and a 5 at the same time? And the answer is no. Okay? There's no card in there where if you draw it, it has a 9 and a 5 on it. You either are the 9 or you are the 5. So these events are mutually exclusive. And when you have mutually exclusive events, all you have to do, so we want the probability of drawing a 9 or a 5. And in this case, all you do is you find the probabilities separately and add them. Find the probabilities separately and add them. So, what's the probability of being a 9? Well, how many cards are 9? There are 4 out of 52. What's the probability of being a 5? Well, how many cards are a 5? There are 4 out of 52. And so since they have common denominators, you can add this real quick. If you really wanted to, you can go to your calculator. So 4 out of 52 plus 4 out of 52 is 8 out of 52. And this is the part where I would go to my calculator and let it reduce. So I go in, I hit my alpha, my y equals. I got 8 out of 52. And there it is. So my probability is 2/13. So I go up here and we'll just plug it in. 2 out of 13. There we go. That's the probability of selecting a 9 or a 5. So right here, the mathematics department of a college has 11 male professors, 6 female professors, 14 male teaching assistants, and 5 female teaching assistants. If a person is selected at random from the group, find the probability that the selected person is a teaching assistant or a female. So again, this is one of those OR problems. Is this mutually exclusive or not? So can you be a teaching assistant and female at the same time? And the answer to that one is absolutely. Right here, look, female teaching assistants. So this is a little different. These are not mutually exclusive events. So let's talk about the probability of this. So we want the probability of being a teaching assistant or female. So in order to do this probability, we're going to find the probability of a teaching assistant. we're going to add that with the probability of female. But the problem is if I do these two and add them together, we're counting those people that are female and teaching assistants twice. So what we need to do is we need to subtract off the probability of a female teaching assistant in the end. Because again, we counted everybody twice. Okay? So, the big thing in this one is, before you can do anything, you got to add everything up. We got to know how many people we have total. So 6 and 14 is 20, plus 11 is 31, plus 5 is 36. Okay? So everything is out of 36. So what's the probability of being a teaching assistant? Well, how many teaching assistants do we have? We have 14 males and 5 females, so that is 19 out of 36. Plus, well, what's the probability of being females? Well, how many females do we have? We have 11 professor females, we have 5 teaching assistant females, so that's 11. Just make sure again, yeah, 6 and 5, 11 out of 36. But now we got to subtract off all those female teaching assistants that we counted twice. So that's 5 out of 36. So all we got to do is some quick adding and then a quick subtraction. So 19 plus 11 is 30, minus 5 gives you 25 out of 36. And again, just go to your calculator if you're not sure. Alpha y equals, and check your fraction. 25 out of 36. And it should be in its lowest form because nothing can divide both 25 and 36. Again, if you're always unsure, you can double check it. So our probability of being a teaching assistant or female, 25 out of 36. Okay. Almost done with chapter 11. So, chapter 12. One card is randomly selected from a deck of cards. Find the odds against drawing a red king. So we want the odds against. So when you're doing odds against, odds are not like probabilities. You will not put this over a total. With odds, especially if it's against, odds against, your top value is the not situation, okay? Not the event. Your bottom value is the event, okay? So it's like you're dealing with complements on this. Or in other words, what we do not want is on top, what we want is on bottom. So when we look at this guy, so we want the odds of not a red king over a red king. Okay? Yeah, red kings. So let's think about this. How many cards, and it's usually easier to answer the bottom part. How many cards are a red king? Well, there are 2 red kings. King of hearts, king of diamonds. And then how many cards are not a red king? Well, 52 minus 2 is 50. So you can see that these are not like probabilities. There's not a total on the bottom. But if you do look at these two numbers and you add them up, you do get the total amount of cards that you had in the deck. Also, make sure that you always reduce your odds. So 50 out of 50 out of 2 reduces to 25 to 1. Okay? So there are your odds, 25 to 1, because 50 over 2 reduces to 25 over 1. And we do need both numbers, okay? So don't just fill in one blank with 25 and leave the other one blank. You need to fill in both. All right. Number 13, you draw one card from a 52-card deck. The card is replaced in the deck, and the deck is shuffled. And then you draw again. Find the probability of drawing a jack the first time and a heart the second. So this is one of those and probabilities, okay? And it's kind of a lot like OR, where you have to think about it in two different situations. You got to know which situation you have. ANDs are all about whether you have independent events or dependent events. Independent events means that what happens the first time around does not affect the second time around. Okay? So for instance, if I go back to my coin and rolling the die story that I gave you for the ORs. If I flip the coin and roll the die, does the flipping of the coin affect the roll of the die? And no, it doesn't. Okay? Those are what we call independent events. Dependent events would be something like, imagine that I have some sort of magical die right here in my hand. It's six-sided, and I roll it the first time, and I get a number, but then all of a sudden that number disappears and when I roll it for the second time. Now that one would be a dependent event, because in the first event, the first roll, I had a chance to roll one of six numbers. After I rolled that number disappeared. Now when I roll again, I only have 5 numbers that could happen. Okay? Because my one side of my die disappeared magically. So that's dependent events, because the first event affected the second event. So when we look at this, if we draw Jack and replace it the second time when I go to draw a card, will that affect my probability of getting a heart? Are they independent or dependent? And they are independent, because I'm replacing it. That means once I put that card back in, there's still 52 cards there. I had 52 cards on the first draw. I had 52 cards on the second draw. So these are independent events, which makes finding the probability easy. So we want the probability of a jack and then the probability of a heart. So all we have to do to find these, since they are independent events, is find the probability of a jack. And then we're going to multiply that by the probability of a heart. Okay? So what is the probability of a jack? Well, there are 4 jacks out of 52. What is the probability of a heart? Well, there are 13 hearts out of 52. So you got 13 out of 52. All we got to do is multiply these bad boys. And again, I just go straight to my calculator, do a little bit of multiplying, but I want to show you what the numbers are. So 4 times 13, because when you multiply fractions, you just go across the top. And 52 times 52. So there, the number 52 up here, this is the numerator. When you multiply it across, this would be the denominator. And then all you would do is just reduce those. So I'm going to write that down real quick and then write the reduced answer, which will be the correct answer. 52 out of 2,704. So when you multiply straight across, this is what you get. Not cross multiply, just multiply across the numerator and across the denominator. And then when you reduce this down, I believe this is 1 out of 52, but let's just make sure. So we got 52, oops, let's get our best friend the fraction. Alpha y equals 52 out of 2,704. Yep, 1 out of 52. So there is our probability. So we scroll back up, we'll just put that in our blank. 1 out of 52. And there we go. I believe this should be our last chapter 11 problem, and then we'll jump into chapter 12, all about statistics. So Elizabeth brought a box of donuts to share. There are 2 dozen, which is 24 donuts in a box, all identical in size, shape, and color. 4 are jelly-filled, 8 are lemon-filled, 12 are custard-filled. You randomly select one donut, and then you're going to eat it, and then select another donut. Find the probability that we will select the jelly-filled first, and then the custard second. So the question is this independent or dependent? If you said dependent, you're on the right track. Because again, in this one, we're not going to replace it. That would be gross because we're going to eat it. If I replace that donut, that means I would have to regurgitate it back up and put it back in the box, and that's just gross. And we don't do that. So these are dependent events because the first outcome is going to affect the second one. Because once I eat that jelly filled, there aren't 24 donuts in the box anymore. Okay? So in this case, since we want to find the probability of jelly filled and then custard filled, here's what's going to happen. We're going to find the probability of the jelly filled first, and then we're going to multiply that by the probability, oops, wrote it wrong. We're going to multiply that by the probability of the custard filled, given that I just ate the jelly filled. Okay? So first things first. Here's our total. The 24, and there are 4 jelly filled. So that's our first probability, 4 out of 24. That's the probability of me selecting a jelly filled and eating it. Now, the next fraction, your next probability, sometimes the numerator gets messed with, sometimes, well, not sometimes, but the denominator will always get messed with. So we'll talk about the numerator here in a second, but let's talk about the denominator. So there were 24 donuts. I ate one, so how many are left? 23. So as I said, your denominator always gets affected, but let's talk about the numerator. The second time around, I want to eat a custard filled. So the first time around, I ate a jelly filled. So because I ate the jelly filled, does that affect how many custards there were? No. So my numerator for the custard filled will be 12. This guy that's right there. And that's what we're going to put in because I ate a jelly filled. So if it was to talk about jellies again, then there would have been 3 because I ate one. If I was going to make a probability for another jelly filled. But because we're dealing with custard, the numerator will be the 12. Unaffected. So just know that sometimes in this second probability, your numerator gets affected. All depends upon what you want to talk about. Okay? So there's what we have to multiply. So just going to go to my calculator, show you what the numerator would look like. Because again, if we multiply across the numerator, 4 times 12 is 48. And then if we multiply across the denominator, 24 times 23 is 552. So there's our fraction. And again, we always want to make sure that it gets reduced. 48 over 552. And that definitely reduces. So let's figure it out. Alpha, y equals 48 over 552. Enter. So our probability is 2 out of 23. And thus ends chapter 11 on probability. 2 out of 23. All right, so let's dive into chapter 12 now. Finish up this exam. We're halfway through. And be done. So, oh, another probability. I didn't think I had one more. Or I guess I do. Oh, so from problem 16 to the end is chapter 12. My bad, sorry. So let's take a look at this one. It says express the following probability as a simplified fraction and as a decimal. So we got to do 2 things. We need the fraction and we need the decimal. If one person is selected from the population described in the table, find the probability that the person has never married or is married. So again, this is an or. So the question is, are these events mutually exclusive or not? Can you never be married and married at the same time? And no, that's just weird. You can't. I mean, if you're married, that means that you're married. You're not never married, so that's just weird. Okay, so definitely in this one, we are dealing with mutually exclusive events. So I need the probability of being married or never married. I think the never married came first up there, but it doesn't really matter since it's an or. Okay? So, let's come down here and let's figure that information out. So, what's the probability of, and again, since this is mutually exclusive, we just got to find these probabilities separate. What's the probability of being married? Well, when we scroll back up there, let's find that total. So here's married. So that's 122 people. The total for that, right over here, 231. So that will be the probability of being married. 122 over the 231. I think it was 231, right? Yeah. Okay, now what's the probability of never being married? Well, let's go find their total. Never being married is right here, and there are a total of 75 people. And again, it will be out of the 231 as well. So 75 out of 231. So we just add all this up, and here's what you get. You got 231 on the bottom, and then across the top you get 197. Okay, so just go to your calculator, reduce this, and make sure that it looks good as a fraction. So alpha y equals 197 over 231. Enter, and it's good the way it is. No reducing on that one. So 197 over 231. 197 over 231. So there's the simplified fraction. Now they want the decimal. Again, it says to 2 decimal places. So we go into our calculator and we need to divide these two now. So 197 divided by 231. So 2 decimal places would be the 5 right here. And what's the 2 say? The 2 says, hey 5, stay cool. So we got 0.85. 0.85. And there you go. Dunsies. Now let's jump into chapter 12. For sure. Guaranteed this time. Okay. It's like I jumped back into the beginning of 15. There we go. So here. And again, everything that we've been doing, everything that you just saw in chapter 11, all went in order of the sections that you were taught from 11.1 to 11.7. Everything in chapter 12 is going to go in the order that you were taught. Okay? So starting out in 12.1, it says the government of a large city needs to determine whether the city's residents will support the repair of several roads. The government decides to conduct a survey of a sample of the city's residents. Which one of the following procedures would be the most appropriate? Now, all of these procedures, you'll be able to get a sample, but does it really represent the population? So as you look at this, let's take a look. It says a survey. So we're going to survey a random sample of residents who use public transportation. Well, I don't think that's going to do us any good because technically those that use public transportation aren't driving, so why would they care one way or another about the repair to several roads? Granted, now they're on the bus and they're going to feel the bumps and the holes in the road and things like that, but those that are using public transportations like the train and, buses and things like that probably don't really care about, some of the conditions of the roads as those of us that actually have a vehicle. So I don't think this one would be the most appropriate. Now again, don't get me wrong, that does give you a sample, but not the most appropriate. Survey every 10th person to use a public restroom. I'm not even sure why you would want to talk to people before they're going into the restroom. They're probably in a hurry anyway. So this one's probably not going to tell you much about whether the public will want to, fix up the roads for those that got to go to use the restroom right away. So you got to throw that guy out. All right, survey the last 100 residents in the telephone book, telephone directory. Again, surveying the last 100 residents, those will be all people that have Z's in there. And some of them may drive, some of them may not, some of them are probably not going to care. So is this the best representation of the city's residents? No. Again, you're only looking at those that are Z's in the phone book. But if you look at D, D is the best one because you're going to survey a random sample of people within each geographical region of the city. So, think about like the suburbs of cities and things like that. This is the one where you're going to get the best representation of your population because we're going to go to each geographical region like Kissimmee and Poinciana and St. Cloud and all that. And we're going to get information from everybody that lives within those geographical regions to help us know should we fix the roads. And that's the best one right there. That's the most appropriate. All right, right here. So they want you to finish constructing the grouped frequency. So this is one where it's kind of like a tally table. That's what I would do at first. And as you go through this, pay attention to these numbers, mark stuff off as you go. That way you know where stuff fits. So I'm going to kind of change the display on this so that way I can see my numbers and my information at the same time. But I need to zoom back in just a little bit more. Say that's still too much. Let me back it out a little bit. There we go. That's a little bit better. So all we got to do is place these numbers into the frequency class that they belong into. Okay. So let's start doing this. So 48 goes into that group, and I'm just going to make tallies as I do this. 68 is right here. This is just one of those problems where it's going to be a little bit of time consuming. So again, all you're doing is just making marks where they go. So, and I'm marking it off as I go along. That lets me know where I'm at and what I've done and what I have not done. It's good practice. And then once we get all these tallies, we're just going to total up the tallies for each one. And those will be the answers that you actually put into the blank. Okay? So we got 43. That's going to go on the upper one. Then you got the 66. So down here. And you just keep making tallies and filling in as you're moving. Make sure that you put them into the right group. Okay? There's nothing crazy about this. It's just, this is what stats is like. It's tedious kind of work sometimes. Okay? So 63 is down in that group. 44. 48. 56. 59. 68. Almost done, guys. Almost there. 51. 60. 68, 62, 64. Of course, you could always speed this up a little bit to get to that end piece. Okay, you don't have to sit here and watch me do all this, but this is exactly what you're going to be doing for this problem. 61, 56, 61, where'd you go? There you are. 62, 46, almost there. 55, 63, 57, getting to the end. 63, 47, and 62. All right, so now I'm going to zoom back in. There we go. So all we do now, just count up what you got. So we've got 1, 2, 3, 4, 5, 6, 7. So in that first blank, you put 7. And you got 1, 2, 3, 4, 5, 6, 7, 8. Second blank is 8. 1, 2, 3, 4, 5. 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6. And there you go. Now, did they tell us how many total there were? Doesn't look like it. Oh, wait a minute. Countries, presidents' ages as of 2011. So, I mean, the best thing that you should do in the end is make sure that everything in this column adds up to the total that you have up here to make sure that you haven't missed anything. But as long as you've been marking as you go, you should be pretty okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This row is the same length as that, so you got 16 and 16. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 16 and 6, or 6 and 6 is 12, plus another 2 is 4, carry the 1, and 44. All right. So let's make sure everything over here adds up to 44. And I'm just going to cheat and use my calculator. So 7 plus, well, we could do this. 7 and 7 is 14. With the 6 is 20. With the 11, that gives me 31. With a 5, that gives me a 36. With the 8 is 44. Yeah, checks out. So I didn't miss anybody. But these are the numbers that are the important ones that will go into each one of those blanks. Do not put tallies in them. They want the numbers. Okay, moving on. See, it was that easy. And I don't think there was a follow-up question to that. Nope. All right, so this guy. So they've done the table for you. You've got this frequency table right here. And I want to know which picture down below represents the histogram for it. Well, all you have to do is match bars. So right here it says at 0, there should at least be a bar of 3. Well, if you look at this guy, there ain't no bar of 3. There's no bar at 0. So definitely ain't this one. It's like process of elimination. If you look at this 0, that's way too high. That's above 10. So it ain't this guy. So we go down here. If we're looking between these two now, again, look at this guy. It's above 10. It's not this one. Oh, process of elimination. There's the histogram graph. It is that straightforward. There's nothing else that you have to do on it. Now, the second part of this question, it wants you to take that picture that you had a moment ago, right here, and I want you to match it to its polygon graph. So let me put these side by side. Scroll over one. So you can see our picture right here. We just want to know which graph over here matches that. Well, obviously we know it's not this guy because, again, I got to be up at 3 and this guy's at 0. Okay? If you look at this guy at 0, way too high. So we know it's not that one. So if we look over here at these guys, now this one looks a little bit closer to 3. This one, it looks a little bit halfway, but let's just double check some other points real quick. So we know that, let's see here, like 1 should just be a little bit lower than the 0. So not as high. And if you look over here, this guy right here for 1 is way too high. It's almost, it looks like at 4. So we know that this has to be the correct picture. This one, all your stuff is just a little bit too high. Okay? And that's it. There you go. That's all you're doing on this problem. Can you take what you already know over here and from the distribution table, that's right up here, and match the histogram and the polygon graph? Cool, moving on. Look at that, we're almost done. Yes. All right, back to single page. So here we want to construct a stem and leaf plot. So I don't like this. This is bad form by our book, but they want you to use commas to separate your numbers. I get it. Also, when you do this problem, we as mathematicians, we like to put our numbers in order, but when you do this one, you don't have to have the numbers in order. Okay, so this one is a lot like what we just did with the frequency distribution table. Okay, all we're going to do is we're going to fill in our numbers. So let me zoom out just a little bit. So there we go. So all we're going to do is take these numbers and put them in our stem and leaf plot. Remember that when you're looking at these, the very last number is the leaf. The number in front of that green line I just drew is the stem. So we know that 1 goes down here with 6. And then I have a 3 at the 4. And then I have a 5 at the 4. And again, directions say put commas, but in a real stem and leaf, you do not put commas. It's all about the spacing and the alignment of your answers. So again, over here, we've got a 4. Again, they're asking us to put commas. That's bad form. We really don't do that. It's all about the alignment. So there's a 1 on the 3. We got a 5 with the 5. We got a 0 with the 4. And again, in math, we like to put our information in order. But for this problem, they're like, it's okay to have it out of order. So you got a 1 there, and then we got a 3 up here at the 2. We got another 5 at the 5. We got a 3 at the 6. So again, you just keep adding those commas. Don't worry about spaces. We got an 8 at the 5. 1 at the 4. We got a 7 at the 6. We got a 5 at the 6. We got a 9 at the 5. We got a 6 at the 4. See, we just knock off that last number, and the first number tells us where to go. We got a 3 here. I know it's kind of messy down there. Sorry. It's much cleaner when you do it in the homework. So we got a 9 at the 3. We got a 3 at the 6. We got a 3 at the 4. We got a 1 at the 4. We got, just doing those together, we got another set of 2 3s up here at the 3. Sorry, I put that on the 2. So 3, 3. We got an 8 at the 4. We got a 5 at the 3. We got a 9 at the 2. We got a 3 at the 4. We got an 8 at the 6. Pumpernickel. There we go. We got a 0 at the 3. We got an 8 at the 3. We got a 9 at the 4. We got a 6. We got a 1 at the 3. We got a 3 at the 4. We got a 5 and a 5 at the 3s. 5 and a 5. And then we got a 3 at the 5. So there's what the stem and leaf plot looks like. Of course, it'll be nicer on your screen than it is on mine. But for the 2s, you got a 3, a 7, a 9, and a 6. For the 3s, you got 1, 9, 3, 3, 5, 0, 8, 1, 5, 5. For the 4s, you got 3, 5, 4, 0, 8, 1, 1, 6, 3, 1, 8, 3, 9, 3. For the 5s, you got 5, 5, 8, 9, 3, 3. And for the 6, you got 1, 3, 7, 5, 3, 8. So then down here on part B, what shape of the display, what does the shape of the display reveal about the ages of the professor? So if you're looking at each example, down here it says the greatest number of college professors are in their 40s. Well, if you look at the 4s, that's pretty true. But let's just make sure that that's the only answer that will work. None of the college professors live in their 70s. Well, we don't know that. Just the sample that we have just isn't in the 70s. I mean, we do have a person that is in the 68, so hopefully they'll live till they're 70. But we don't know for sure that none of them live till they're 70. And if you are younger than 30, you cannot be a college professor. Well, that's not true because I have people up here that are younger than 30. I've got 4 of them that are college professors. And then D, none of the above. Well, that doesn't make any sense because we found that A actually works. Okay? So let's jump to the next problem. And those are your longest problems right there. So now everything from here on down, all about using that calculator like I showed you the other day. You can plug in these numbers into STAT. So the 77, the 74, the 76, the 69, 74, and 80. You can just go right in here to your STAT and plug those numbers in the list. So you'll put them all right here in the list, or you can just run the formulas that you know for them. You don't always have to plug them in the list, but let's just talk about the list real quick and review that real quick on how we can do that. So we've got 77, 74, 76. So again, I hit Stat, and we're going to work under Edit. So we got 77, 74, 76. And then, oops, minimizing everything. So then we got 69, 74, and 80. 69, 74, and then 80. So there's all our values. And then all we want to do is run statistics on this. Okay? So to run statistics, hit Stat, scroll over to Calc. And we're going to work right here at this guy that's right there. So let's open that up and let's talk about it. Oh, remember to hit Enter 3 times right here, or scroll down twice and then hit Enter. So this screen right here, remember that X bar represents the mean. Right here, this is sigma X, which means that this is what we would get if we add up all the entries, the 77, the 74, and so on and so forth. These two right here, they represent the standard deviation. But this is the one that we're going to use in this test and that you use in your assignments and everything like that. Use the S of X because we are a sample. The N right there, that's how many entries we had, and there were 6. This little arrow means scroll down. So then right here you can see the smallest entry value. So you don't have to put it in order. So our smallest data value was 69. Right here is the median, so that's the middle value, which was 75. And then right here, this was the largest value we had, which was 80. So when we go back to this question, and you can do that on all of these questions that are coming up right here. So it says find the mean. And it wants us to round to 3 decimal places as needed. So we just go back to our calculator. Remember, the mean in the calculator was the X bar. So what's the mean? 75. So that's what we put in the blank. 75. And then we move on to the next one. Again, if you were doing the mean by hand, all you would really do is take 77 plus 74 plus 76 plus 69 plus 74 plus 80, and then divide all that by 6. That's how you find the mean. Add it all up, divide by however many there are. Again, that's your X bar. All right. Median. Again, you can go straight into the calculator, put all these numbers, and figure it out. But you can also just do it quickly by hand. I mean, just put your numbers in order. So 28 is the smallest. And then you got 29, 29. Marking these off as I go. Oh, I had a 27 up there. Kind of snuck in on me. Let me adjust these over. Whoa. Go back where you were. Stop it. Okay, hold on 1 second. Grab this guy. Lock you in place. There we go. Now I can grab my stuff. We'll just slide all this stuff over. There we go. All right. So then we got a 30, a 31, a 33, and a 34. And all we're going to do is work our way right into the middle. So I start at the 27. You can see my finger there. See how it popped up? I'm going to start at the 34, and I'm going to jump my way in. So the 27 and the 34, we jump to the 28, 33. They cross each other out. We jump to the 29 and the 31. They cross each other out. Oh, we're stuck between these two as we work to the middle. Well, how do you find the median when you're stuck between two numbers? All you have to do is add them up. Oops, I about wrote 20. Should be 30. Add them up and divide by 2. So if you added those up and divided by 2, you would find out that it is 29.5. That's the median. And again, you could just put this in the calculator if you wanted to. Okay, and run your one variable statistics in the calculate. So there's number 21. All right, number 22, mode. What number occurs the most? That's what mode is. So notice there are two choices down here. There is a mode in this, so you would actually select choice A, and then all you got to do is tell me what the mode is now. So what is the number that occurs the most? These are the same numbers that we had just a second ago, and that would be the 29, because it happens 2 times. Everybody else only happens once. There's your mode. All right. Mid-range. So remember mid-range, when you talked about it in class, mid-range is really easy to find. All you're going to do is take the smallest, oops, if I could spell right today, the smallest entry, add that with the largest entry, and then divide by 2. So what's your smallest number up there? It is 88. What is your largest number up there? 94. So all you're going to do is add those 2 numbers up and then divide by 2. And off the top of my head, I don't know what that is. So let's just clear this out. We got 88 plus 94 divided by 2. And there it is. So our mid-range is 91. Okay? 24. Find the range. Again, range is not hard. Take the largest entry minus the smallest entry. So what's my largest entry? 10. Minus what's my smallest? 4. 10 minus 4, 6. And there you go. There's your range. See, a lot of these middle questions, real quick. Not much that you have to do. All right. So 25. Find the standard deviation. Okay, in class, hopefully your professor, I know I did this. I showed it once by hand. Other than that, I tell my students, let the calculator do this. So we're going to go on the calculator, and we need to put 4 17s and 4 13s. All right, so I'm going to go into my list. Stat. Edit. Oh, I already got a list in there. If you want to get rid of that, all you got to do is hit clear. And then hit enter. Well, there we go. And now all we just got to do is put 4 17s and 4 13s. Again, it doesn't matter the order. So there are my 4 17s, and now we put in the 4 13s. One more. And then all we do is run calculate for our data. So hit stat again, scroll over to calculate. 1 variable statistics. Enter, enter, enter. One more time. And now, right here, is the standard deviation. That's what we want. So let's check on the rounding. What do they want us to round to? So it says round to 2 decimal places. So we go back. 2 decimal places would be 3, and the 8 says, hey 3, take it up. So you got 2.14. 2.14. There's your standard deviation. 2 more, and we're done. Yay! So, in here, it says not everyone pays the same price for the same model car, same model of a car. The figure illustrates a normal distribution for the prices paid for a particular model of a new car. The mean is 23,000 and the standard deviation is 2,000. So using the 68, 95, 99.7 rule, find what percentage of buyers between what percentage of buyers paid between 19,000 and 27,000. So in this one, Down here, they show you who's in the middle, so that's the 23,000. Okay? And what we care about is being between 19,000 and 27,000. Well, where's the 19,000? Right there. Where's the 27,000? Right there. If you follow those lines up, you now know what the percentage of those people are. 95%. That's what they wanted. Okay. And then last but not least, we got a quick Z-score problem for you. So it says the scores on a dental anxiety scale range from 0, no anxiety, to 20, extreme anxiety. The scores are normally distributed with a mean of 11 and a standard deviation of 4. Find the Z-score for the given score on the denial anxiety scale. So the Z-score is just telling you how many standard deviations your score is away from the mean. So if you want to find a Z-score, this is what you have to do. You're going to take your data minus the mean, all of that divided by the standard deviation. And they provide all that work for you. What's our data score? It's 14. What was the mean? It's right there. It's 11. What was the standard deviation? It was 4. So you just go to your calculator and you run the quick information. And again, it says type an integer or a decimal. So we're going to go to our calculator. We're going to take 14 minus 11, which, if you can't do that in your head, that's 3. And divide that by 4. Which, in your calculator, if you take 3 divided by 4, you get 0.75. And you don't round that. They want everything. And that's it. There you go. That's how you find a Z-score. Take your data minus the mean. Divide that answer by the standard deviation. And that, ladies and gentlemen, is the Chapter 11 and 12 Exam 3 study guide. Good luck.